Alright, let's get started talking about statistical inference. The objectives for the session are that you will be able to articulate the role of statistical inference in informing clients' decisions, be able to describe the step-by-step process for testing a null hypothesis, and finally be able to do hypothesis tests in Stata. Now, Stata will do the calculations you ask for, but you still need to do the hard work of correctly interpreting those results and the implications for the client's research questions. So the data that we're going to be using in this session comes from the Educate Girls Development Impact Bond evaluation that ID Insight conducted between 2015 and 2018. In that evaluation, we were trying to answer the question if Educate Girls in-school volunteers improved learning for students in grades 3, 4, and 5 in government primary schools in Rajasthan. The data comes from 6,837 students across 332 government primary schools in Bhilwara district, Rajasthan. And the data that we're going to be looking at includes baseline test scores and annual follow-up test scores for students for those 3 years, as well as some student demographic data and whether the school they were in was a treatment school or a control school. And you can find this data linked at the bottom of the Statistical Inference Bootcamp webpage. In this lesson, we'll start by talking about why we do statistical inference, and then about the central limit theorem and why it's important to understand it intuitively in order to correctly interpret statistical analysis. We'll walk through the intuition behind testing a hypothesis and the types of hypothesis tests we typically do at ID Insight. Then we'll go step by step through the most common hypothesis test that you'll be doing, which is testing the equality of means. Then we'll talk about how to do one sample hypothesis tests in Stata, and conclude with 2 sample hypothesis tests in Stata. So let's start with why we do statistical inference. So in all of our engagements, our client wants to know something in order to make a more informed decision. For instance, in the new incentives project, the client wanted to know if conditional cash transfers improve immunization rates in northern Nigeria. In the IDERI project, the client wanted to know what percentage of rural adults in West Bengal and other states in India used an Aadhaar ID to open a bank account. That's something our client wants to know is called a population parameter. However, that population parameter is often unknowable because we can't collect data from all individuals in the population at all points in time. And so our job is to come up with the best possible estimate of that parameter using a representative sample of individuals from the population and an appropriate estimator to back out the estimate from that sample. So the first estimation input that we need is a representative sample of the target population. And we sample because it's usually not possible to collect data from everyone. And sampling takes different forms and different engagements. For instance, in a needs assessment, we may sample individuals from a population for our study. Within impact evaluations, we sample individuals to be either in the treatment group or in the control group, since it's not possible for them to be in both. And even in some sense, the population that we observe at any point in time is a sample of individuals' outcomes at that point in time and is representative of the larger population of anyone who may receive this program or be influenced by this policy in the future. So because we sample, our estimate necessarily includes statistical noise, also known as sampling error. And so if we were to take a different sample, then we would get a different estimate. Hopefully that difference is pretty slight. We don't want to be giving our clients an estimate that is primarily made up of noise. So we'll be talking about how to select a sufficiently large sample and other measures you can take to make sure that the noise is not dominating the signal in your estimate. So the second estimation input that we need is an estimator. And an estimator is a rule when applied to a sample produces an estimate. Notice the similar terminology here. Estimator means a rule or formula. Estimate is the specific quantity that we're getting from our sample. And then sometimes you hear the term estimand, which just means population parameter, or the true population value that we're trying to estimate. So what are some estimators from our work? There's the sample mean. For instance, if we want to estimate student performance on a test, we could randomly sample some students from the population and calculate the average score. There's the difference in differences estimator. So say we want to estimate the effect of an education intervention, we could collect baseline and inline test scores on treatment and comparison students and then calculate the differential change. And a third very common estimator is the ordinary least squares estimator. So say if we want to estimate the effect of that same education intervention, instead of calculating the differential change between treatment and control, we could instead run a regression of inline score on treatment, binary, baseline score, and other variables, and calculate the coefficient on the treatment variable. And notice that that will likely give you a slightly different value than if you had applied the difference in differences estimator to the same data. Unfortunately, one of the unavoidable truths of sampling and estimation is that you will never know if your particular estimate is too big or too small or really close to the true population value. The one saving grace is that we can use statistical tools to say how likely it is that our estimate is a certain distance from the true population value. In other words, you can't ever know, but don't despair. Statistical inference can help you get there with only a little margin of error. The fundamental tool in statistical inference is the hypothesis test. So say you're trying to estimate the impact of an education intervention. So you run an RCT and calculate an average treatment effect of 0.3 standard deviations. The hypothesis test is not going to be able to tell you for sure whether your estimate is within, say, 10% of the true average impact of that intervention. But it will be able to tell you the probability that your estimate is within 10% of the true impact. And that probability ends up being really useful to decision makers. If you can tell a client, I estimate the average impact of your program is 0.3 standard deviations, and it's highly likely that the true impact is within 10% of that estimate. Versus if you say, this is my estimate, 0.3 standard deviations, and it's possible that your program's impact is as high as 0.6 standard deviations or even 0. See, that's a big difference. That level of confidence in your estimate can influence whether the client decides this program is worth investing a lot to scale up, or, I need to shut this program down, or if more work needs to be done before they can really understand the impact of the program in order to make a decision. So understanding the theory and mechanics of hypothesis testing is going to be critical for interpreting results accurately for our clients.